Okay, so here we are again at the end now of our neural network discussion, which took us 2 sessions and multiple videos. Last we talked about adversarial attacks on neural networks and their importance for society. And now I just have a few general questions for discussion. So this will now not be any new content, but what we do now, perhaps you should be prepared to stop this video at multiple points when I tell you. Think about it. This is a kind of tutorial session. I will give you some questions to think about. You should think about these questions and try to come up with your own answer, and then perhaps compare with the answers that I will give you here. So one question, if you have understood, make sure that you understand these things, that you can answer these questions, because this is how you make sure that you have actually learned what you're supposed to learn. If you cannot answer these questions, go back and listen to all the neural network videos again. So one question would be, describe how information is stored inside a neural network, artificial neural network, right? It's ANN. Can you look inside an artificial neural network and see what is stored there? This is a very elementary question, but still, of course, most people who don't have training in neural networks get this wrong. So, and this is very important for questions of responsibility, ascription, liability, ascription for neural network designers. So try please to do that. Describe how information is stored. Can you look inside a neural network and see what is stored there? Stop the video for a moment and then we will answer the question. Okay, so I hope you could give an answer yourself. The neural network contains no symbolic representation of the stored information. It means you will never find in the neural network anywhere a string, giving you the content of what has been learned. The information is instead stored as a vector of synaptic weights that looks essentially like that, numbers between 0 and 1. This vector can only be interpreted by that particular network in combination with particular learned inputs and desired outputs. This vector doesn't make any sense outside of this network, because every number is one synaptic weight, and the synaptic weight is the synaptic weight of this particular neuron that is connected to these other particular neurons and has learned to produce a particular output given a particular input. So if I don't have the right inputs or outputs, even if I have a fully trained network, I don't know what it's doing. Is it recognizing faces? Is it listening to an audio file? Is it emulating logical functions? It's hard to say, right? Logical operators, it's hard to say what it does. It's impossible to say what it does if I don't know what the expected outputs are and what the kind of expected inputs are, right? And also if my network has a different number of neurons, a different number of layers, then all these numbers don't mean anything anymore, right? Because they work only in combination with this particular neural network that has the particular synapses at a particular layer, right? Obviously, if I switch the layers around, it will not work in the same way, even with these weights, right? So there is no symbolic of human-readable information anywhere inside the network. If you are given a network fully trained and asked, what does this thing do? You will not be able to say. Impossible, in principle. You would have to try all sorts of crazy input patterns, billions of input patterns from all areas of human experience in order to try to find out what this thing is doing. It's impossible, right? So how can I check then what the neural network has learned? I have trained a neural network to recognize handwritten letters. How can I see exactly which letters it has learned? Again, stop here for a moment. Try to think about it yourself. I cannot, is the answer. I cannot. There is no way to list the information that is stored in a neural network except the vector of its synaptic weights. This is all we have. If I want to know what's stored in it, I have to apply test patterns as inputs and see what the network will output. I have to apply test inputs and see what it will output. Then I know what it has learned. This is the same situation as testing learned information with human students, right? Because your brain is a neural network. It's the model of all neural networks, right? And your brain has the same limitation. If I want to see what is in the brain of a student, I cannot just open it up and look at the synaptic weights. Let's assume I had a way of reading the synaptic weights out of your brain in with a kind of helmet that could read every synaptic weight out of your brain, which we cannot. But assuming I had such a science fiction device, still it wouldn't help me. I would get billions and billions, 100 billions or more, 1 trillion synaptic weights. And now what? What does this encode? Some of them encode pain signals. Some of them control the movement of your arms or fingers. Some of them process audio from your brain. Some of them process input from your eyes. Some of them do all these things. They just connect different areas of the brain doing different things. So where is the information you learned in this class? Where is it stored in this trillion synapses? You cannot say. Right? It's somewhere. And you cannot say what it is. So the only way how I can know whether you have learned something is to give you a test pattern, and this is called an exam. I give you a test input, which is a question, and you give me the output of your neural network for this input. And then we compare, just like in backpropagation, I compare the expected output, which is my model answer, with your output, the real answer, and the error is the grade you get, essentially, right? The inverse of the error. So if the error is 0, you get an A. If the error is a little bigger, you get a B. And if the error is too big, you get a C, right? So this is why we need exams. We cannot list the information stored in human minds. And in the same way, we cannot list the information stored in neural networks. So the fact that we cannot look inside neural networks means that they can surprise their designers. For example, when AlphaGo in the second game against Lee Sedol made a surprising move 37. This is a famous move. You can look it up on the internet. No one had anticipated that or even understood at that time, right? It made a move that the people who programmed it could not understand, and they didn't know that this would happen. And you can look it up. There's a whole article about this in Wired, for example, but also other sources. This is a very strange move, said one commentator, who was a professional Go player. I thought this was a mistake, said another. And a master player who helped train AlphaGo kept saying that this was a very beautiful move. But none of these people anticipated this move, because you don't know what happens inside that neural network, right? So this can be said to be an example of creative behavior that no one could anticipate. So perhaps we are looking also for creative behavior in the wrong places. We are normally associating creativity with painting, right? Perhaps making an unexpected move in Go would be an example of creating behavior. Now, every system is embedded in an environment. For artificial neural networks, the environment provides the inputs to the system and interprets the output. Compare now the role and the importance of the environment for symbolic AI systems and artificial neural networks. How are they different in respect to the environment? I'm listening. In vain. Here's the answer. Symbolic systems can be complete without any environment. I can program Psych, let's say, my expert systems, program it completely, have it ready there, sitting in the computer waiting for an input. It doesn't need an environment. They are just a set of predicate calculus expressions. These expressions can be written down into a program by a programmer, even if the system has no contact with an environment. The system can be operated in isolation, or it can even never be switched on, right? We could have a system that we never switch on. It will still be a complete system. Neural networks are different because they don't make sense without an environment. You cannot have a neural network without an environment, because when they are first configured, the synaptic weights are random, so the neural network does nothing interesting. All the behavior of the neural network has to be learned from its environment. which can essentially be the programmer providing input and output patterns, but it is the environment. It is the input and output patterns. You cannot program it by directly entering values into the synapses. The neural network does not contain any information before it is switched on and trained on environmental inputs. It doesn't contain any information. So therefore, the environment is crucial to the neural network. You cannot have a neural network that has never seen an environment and say this is a neural network. This is one, but it's not trained. It's random. If you want it to be trained, it has to be trained through the environment. Now, how does reinforcement learning change this? Are reinforcement learning systems philosophically in any interesting way different from normal artificial neural networks? What do you think? Yeah. So with backpropagation neural networks, you have distinct learning, training, and operation phases. You first learn, then the network is trained, then it goes to operate. Reinforcement learning goes one step further, because now the network is not completely trained at the moment of deployment. It continues to learn during its normal operation. During operation, the network tries out new behaviors. If these behaviors lead to good results, they are reinforced. That is, the network is encouraged to use them again. If they lead to bad results, they will be avoided in the future. They lead to a punishment signal, so the network will not use them. The network determines itself whether the results are good or bad. So, for example, in an elevator, by measuring the mean waiting and transport time for passengers between pressing the call button and their arrival at the destination floor, the elevator can optimize its behavior by waiting at the optimal floors. So this means the elevator doesn't need to be supervised. It can itself determine which results are good or bad. But then reinforcement learning lifts the distinction between the training and application phases, which you find in traditional neural network concepts. The system learns inside its final operating environment by exploring available action alternatives in a trial and error fashion and optimizing its own parameters according to the results. Now, why is this significant? Because therefore the exploration phase is an integral part of the design of the working machine, and it cannot be separated from it. Right? You cannot say, I have a learning exploration phase and I have the working machine, and the machine will make mistakes in the exploration phase, but when it works it will be free of mistakes. This doesn't work. This machine will make mistakes while it operates, because this is the way how it learns in reinforcement learning. In order to learn, it needs its punishment signal. How does it get the punishment or the reward signal? It gets it from acting and then doing something wrong and then getting a punishment signal. If it doesn't get a punishment signal, it doesn't learn. So therefore, if you want a reinforcement system to actually do something useful, to learn to do something useful, it has to make its mistakes, like a human being. So this is necessary in highly dynamic environments where a system needs to change continually in order to achieve optimal efficiency. This is what we said about the elevator. If you don't remember, go back to the reinforcement learning topic, a few videos back. So since learning is done by trial and error, you find that errors are unavoidable features of any reinforcement learning system. You cannot have reinforcement learning without error. This is quite contrary to the common traditional understanding that technology, if done correctly, must operate free of errors, and that errors are always the error of the programmer, not of the programmed machine. This is not true anymore. In reinforcement learning, we have for the first time the necessity of errors as we know it from living systems, as a system feature and not only as a product flaw. Right? The error is a feature of the system. The error is what makes the error signal, the punishment signal, which comes, the negative reward which comes after an error, is what the system needs in order to be able to adapt and to operate in a dynamic environment. So it's not a product flaw. There's nothing wrong with the system that makes errors. It's perfectly, finely working and learning. And so you cannot demand that the system be free of errors if it is a reinforcement learning system. So now the question is, of course, if reinforcement learnings are so prone to errors, why would we even use them? Why not get rid of them and use conventionally programmed systems that are more reliable? Because we as a society need these systems. Where do we need them? Dynamic, adaptive elevator control in big buildings. Without that, we would forever wait for elevators. In a building of 90 floors, which you have all around the world nowadays, multiple of them, it would be almost impossible. You would wait half a day, for your elevator if you didn't have an adaptive system that knows where to go in order to minimize waiting times. Diagnosis of diseases in situations where there are no doctors available. Without such systems, we would have people die from undiagnosed diseases, which is worse than the occasional wrong diagnosis. Self-driving cars. Without them, we would have to accept all the failings of human drivers. Self-driving cars are great because human drivers are so terrible. And, I am one myself, and I know how bad I am. Human drivers are very unsafe drivers. They drive when drunk, they drive when distracted, they are unreliable, they have insufficient sensory organs, they have bad eyesight, they don't hear perfectly, they cannot see what is on the back, they have bad judgment, they have slow reflexes, they have all kinds of emotions while driving, they are aggressive, they are sad, they are occasionally perhaps crying, coming from a funeral, they have all kinds of conditions that would make it very unlikely that they drive well. And because there's so many of them on the road, and you need only one somewhere close you in order to crash, this causes a high probability of causing accidents. And street traffic is one of the big killers of humanity, right? So obviously, self-driving cars are a great benefit to humanity. If we can manage to make them work, we will get rid of all these totally unnecessary deaths. So this is why we need reinforcement learning systems. You cannot say these are unsafe and just not use them, because if we don't use them, we get an even worse deal. We are stuck in a situation where we don't have all the benefits, and we need those benefits. So as in these cases, reinforcement learning machines, despite their problems, are the better option, because having an elevator or a Tesla car occasionally kill someone is still better than having humans kill other humans all the time because of their bad driving, right? So we will need to accept the errors because we want the benefits. Now here's a more tricky question. A symbolic AI system and a neural network are both programmed to steer a robot car. Now both crash into other cars on their first real drive, injuring other people. You are the judge. Both programmers say that they are not guilty for the wrong behavior of their systems. What do you think? Do they get the same sentence, or are they responsible to different degrees? The programmer of the symbolic AI system and the programmer of the neural network. This is a very important question for AI in society again, because this is what society will have to do. We already have crashes with self-driving cars, and we have judges that are stuck in this situation trying to assign the blame or the legal liability to somebody. To whom? Now, the symbolic programmer has entered every rule and every command of the program into the machine himself. He has had access to the whole program, could inspect it, and he could test it. The neural network programmer taught the network to drive by example. At no point did he have the possibility of inspecting the program's stored information, because this is just a vector of synaptic weights. He could just train it long enough and then test if it could cope in real-life situations. Such a test can never be exhaustive, because like with adversarial patterns, life provides you with adversarial patterns all the time, unanticipated patterns. So you perhaps have not thought to test the car when it's at the same time snowy and sunny. This can happen. You can have a cover of snow and sunshine. Now this produces a very strong light, glare, which the cameras see as perhaps as a glare artifact, right? A white spot somewhere in the image. And this white spot makes the car think that perhaps this is a traffic sign, and the neural network interprets it as a stop sign and suddenly stops, right? This is entirely possible. And you couldn't have predicted that as a programmer, right? It could be, here you could still say, okay, perhaps a programmer should have thought of that. But you can be driving on a street and suddenly, a little dog comes dressed as an elephant because it's Halloween. And the crazy dog owners have dressed their dog as a pink elephant. And now suddenly a pink elephant is crossing the street. What is the neural network supposed to do with that? Right? You cannot have trained it possibly to recognize this correctly. So it will get some misclassification. Something else will fire there because there is no output neuron for, pink elephant, dog dressed as a pink elephant. It's possible, even if especially if it has, perhaps some crazy patterns painted on it. It's not pink, but it is, in some kind of psychedelic pattern, color pattern, that this will be an actual adversarial pattern that will cause the neurons to misfire. You get a wrong classification, and the car accelerates and kills the dog, flattens the elephant. So this can happen, right? You cannot really hold the programmer responsible. You didn't test it with little dogs that are painted to resemble elephants. What kind of accusation is this, right? What follows is that the neural network programmer should be justly held less responsible than the symbolic programmer, right? He has less control over the thing. The same applies to all learning software, even if it's not neural network based. So the Microsoft Tay, for example, is a famous example of this. On March 23, 2016, Microsoft unveiled Tay, a Twitter bot that the company described as an experiment in conversational understanding. So Tay would chat with you on Twitter, and the more you chatted, the smarter it got, because it learned from users what to say, and it stored the users' responses and then used them itself. So the idea was it would become more and more human through casual and playful conversation. Soon after it launched, people started, as the internet is, and the human society is, one must say, unfortunately, started tweeting the bot with all sorts of misogynistic, racist, Donald Trump and other remarks, of this type. And Tay stored everything, because this was what she was supposed to do, right? Or it was supposed to do. It stored everything in its database and started giving these sentences back to users. And after a while, it produced sentences like this, I hate feminists, they should all die and burn in hell. Hitler was right, I hate the Jews. And immediately, of course, Microsoft, terrified, switched it off. It disappeared and was never again mentioned. And everybody tries to forget that this thing ever was put up there. So it lasted less than 24 hours, the whole life of Microsoft Tay. And this is what you have a problem when you train a system through an environment that is not controlled sufficiently. If the training environment is under the control of the designer or the programmer, then he can decide what input patterns to use. But if the environment is an open environment that trains your program, then you have a problem. And who is responsible now? Who is responsible? Is it Microsoft? It doesn't seem to be Microsoft, right? It's not fair to say Microsoft did something wrong. Microsoft did nothing wrong. It's all these millions of people on Twitter, of which, most of them are just perfectly normal people, but some of them are crazy, stupid people who will say these things just to cause the robot to misbehave. But you have such people, and they are there. And so we have to do something about that. We cannot go on training robots in real environments if the real environments are populated by people who say such things. So the programmer cannot be responsible. Microsoft cannot be responsible. They couldn't even have predicted this, right? It's always easy to say now they should have thought of that. Back then, perhaps they couldn't have thought of it. And who is responsible? Everybody who talked to Tay is responsible to some extent. The people who produce these utterances about feminism and Jews, these are responsible, but these are gone. You cannot catch them. You don't know who this was. And probably there were thousands of them. And each individual utterance didn't cause much of an effect on Tay. But thousands of these utterances. Then Tay stored that this was a common utterance and something that it could say back. So every single individual user has perhaps a thousandth or a tenth of a thousandth of a responsibility for a particular reply. But all together are responsible for Tay reacting like this. So you have a question of aggregate responsibility. What happens if people are not individually responsible but responsible as a group? What does this mean? Are they legally liable as a group? Can we, pursue them as a group? Can we try to get damages paid from them as a group? Should each one contribute 1 cent then towards a fund which will be used to pay for the victims of some AI activity? It is very difficult to sort out these things if you have an anonymous population of users being responsible for the training of a machine, right? We will talk more about this responsibility and liability problems later, but this is a crucial thing that happened there. It's a very important case, and you should remember this. Okay, so let's finish the whole neural network thing with a brief summary. So neural networks are able to learn. They are able to perform well on problems where the programmer doesn't have a symbolic or algorithmic solution to a problem, like character recognition. It's difficult to do with an algorithm. They can perform in new situations where they have not learned. Their behavior in new situations might not be optimal, but it's better than the breakdown of a brittle symbolic system. Winograd has introduced this idea of brittleness. Neural networks can have direct access to sensory data, and so they can provide symbol grounding for further symbolic processing for hybrid systems. So this is a way of creating, systems that have the advantages, but also the advantages of symbolic AI. So you can combine a neural network with a symbolic system. You can say, I get sensory data, process them with a neural network, sound and vision, and then I create symbols out of these data and feed them into symbolic systems. So I take psych with a neural network sensory front end. And then I get something very much like us, right? Because, as we said before also, we are not purely symbolic. We have all these neural networks that process sensory data. But we do have symbolic processing. Right now I'm talking in a language, and the grammar of this language is a symbolic structure. The language on my screen is symbolic. When I'm making calculations, I'm processing symbols. When I'm thinking of what I will do this afternoon, I'm processing symbolic entries in a calendar. So all these are symbolic processing. So we do have symbolic processing and sub-symbolic processing together integrated into our brain, right? Parts of the brain do symbolic processing, parts of it do sub-symbolic neural networks. And so we can imagine that perhaps we could create hybrid systems that work in these both in these ways, right? And have the advantages of both. Now the drawbacks of neural networks. Again, you can stop the video if you want. Think about it for a moment. One problem is that depending on the training, they can come up with strange answers. There is this story, I don't think that it's a true story, but it's a very famous story, and there are similar stories that are true stories, so it doesn't hurt to recount this story. When an early neural network was supposed to be used in the Cold War, and they tried to train it with images to recognize tanks hidden in the forest, Soviet tanks, right? And so you would have images of forest, and sometimes in the forest would be hidden a tank, and you had all the satellite images of the forests, and because nobody wanted to look at so many images, you would have a neural network look at these images and say, here is a tank, here is a tank. And then they trained the neural network, and again, this is probably not a real story, but it's a good story in the sense that it shows what the point is. So they trained this with different images, with tanks and without tanks, and it was always able to recognize correctly when there was a tank in the forest. So the military was very happy. This is really paying off, and we can from now on, scan all the forests of the world for tanks. And then they gave it a new set of images that they hadn't used before, and it completely failed. And recognized tanks where there were no tanks, and failed to recognize tanks when there were tanks. And so what went wrong? And they were trying to find out what went wrong, and they found out finally what was wrong is that all the pictures with tanks had been taken on sunny days, while all the pictures without tanks had been taken on rainy days, because they just went out one time to take all the pictures. And therefore, the neural network had just been trained to recognize sunny picture or rainy picture. And when later they got pictures from a second batch, which were filmed under different conditions, the network completely failed because it was recognizing sunny and rainy, not tank, no tank. Now, it doesn't matter whether the story is true or not. It could very well have been true. And there are true stories, very similar true stories that do happen all the time when you train a neural network, because you never know which features you are training. If your training sample is good, then you will have all the noise equally distributed among your pictures. But it's difficult to do, right? Very often you will have some kind of noise that you are not aware of, that you have introduced into your pictures, and that the network might pick out as a feature because it's a reliable feature in your data, and it will learn this, right? In the end, what networks learn is a statistical thing. Networks learn to distinguish the inputs according to some feature. The feature that the network finds useful might not be the feature that you find useful, right? So it might learn to recognize your uncle because your uncle is always wearing a green t-shirt, and the only person in your family always having this terrible green t-shirt is your uncle, and the network learns to recognize the uncle. But because the uncle is always wearing green and he's the only one wearing green, for the network it's much easier to recognize the green t-shirt. It leads to a success in training. It leads to a reduction of the error. So the network can perfectly happily recognize the t-shirt while training, and not the uncle. And later, if somebody else wears the t-shirt, he will be recognized as the uncle, right? It's a misclassification due to a bias in the data. And it's very difficult to get rid of these biases in the data, right? It's very difficult to make sure that all the backgrounds are always different, that all the colors of the clothing are always different, that people don't have, that the same person has different kinds of hair on them, sometimes with beard, sometimes without, sometimes with long hair, sometimes with short hair, because you want to be able to recognize them, and so on. So good training is crucial. Neural networks can be difficult and slow to train well. We can never reliably tell if they are trained well, right? Because there is no way to fully examine the effects of neural network training except by testing the reactions. So if the networks learn while deployed, the environment itself becomes a trainer for the neural network. Therefore, the programmer has no control over what the network will learn. And the same applies to all learning software, even without networks like TE. Right? If the network learns while deployed, the environment becomes a trainer, and the programmer has no control, because now the program is gone from the programmer's control. In the case of reinforcement learning, errors are an integral part of the system's operation. So this makes it worse, because there cannot be an error-free reinforcement learning system. In the same way, like there cannot be error-free humans. We learn from making errors. If you want a human who never makes an error, it will not work, right? Learning, exploration, and error go always together. Okay, and that's it for the moment. Thank you. We are finished with neural networks. Next time we talk about something else. See you.